Okay, hello. Last week of this semester, I think I promised a long time ago that we weren't going to do any more Fitch-style proofs, but here we are. I assigned, who knows when, before break I believe, this worksheet called Peano Arithmetic Fitch-style proofs. And it's exactly what it says. It's a bunch of proofs, two really, in Peano Arithmetic, so using the language of Peano Arithmetic, and the axioms of Peano Arithmetic, to execute some simple proofs, but doing it Fitch-style. And okay, the Fitch-style framework simply forces us to do the proof properly. The sort of two strands of this class have now met, and Fitch-style proofs, which we've been doing all semester, they don't become a thing until maybe say 1940, but formal axiomatic proofs in which the sentences are written in first order logic, and every sentence has been in some kind of precise syntax. That is around now, in the 20s and 30s, while people are trying to prove certain things about Peano Arithmetic. So we've sort of come together now. So if you're going to do one of these proofs, you might as well do it all the way according to some extremely exacting standard of rigor. So that's what we're going to do. All right, what are we going to prove? We're going to prove the mind-blowing fact that 1 plus 1 is not 3. And okay, while we do this proof, this is not going to be mind-blowing or anything, but it is going to give us some understanding of Peano Arithmetic. After all, one sort of only finally understands, you might say, the axioms of some theory when you see them in action. So the axioms of Peano Arithmetic, when presented to you, might seem very plausible, and you might agree that they're true, but you really don't understand what role that axiom is playing until you start to see how that axiom is used. So okay, this is very similar to some things we did in class the very day that we were doing Peano Arithmetic, but we didn't waste our time then making it precise according to a Fitch-style proof. So let's do that now. And the Fitch-style proof is just going to keep the whole enterprise honest. Alright, enough rambling, we begin! What do we have here? Well, I started the proof already with 4 premises, and these 4 premises are 4 of the axioms of Peano Arithmetic. And they're the only ones that we need. So there are others, but I'm just not listing them right now because we don't need them. And what are the axioms? Well, the first one says, so S is the successor function. It's a symbol. It's a function symbol. It takes some element from our domain, which we think of as being the natural numbers, and gives us some other element, the next one. Okay, but in our logic, it's just a symbol. It's a function symbol. And okay, what does this say? This says that for all x, the successor of x is not 0. Okay, so another way of putting this is, there does not exist a number whose successor is 0. Yeah, it's just exactly that. Okay, so good. That is the sort of fact about 0 that you need to know. Then there's this one. This says that the successor function is 1-to-1. If 2 numbers have the same successor, then they must be the same number. Some people find the contrapositive of this easier to reason about. The contrapositive is if 2 numbers are different, then they have different successors, which is how the successor function works. It's supposed to give us the next number. So 2 different numbers can't have the same successor. And 3 and 4 are not axioms of Peano Arithmetic strictly speaking, or arguably they are. It depends on how you look at it. They are the definition of addition in terms of the successor function. So not everyone uses this nowadays, but you certainly can define addition as kind of, what is addition really? It's sort of like adding 1 or something, and that's what the successor function does. So one may define addition recursively in terms of the successor function. That's what we've done here. What is this whole addition thing? Well, it's a binary function, and if you want to be kind of a weirdo or something, you could force, if you're trying to force the issue and to force yourself and everyone else to recognize that addition is just a binary function, then you could write it in a kind of stylized way where you put the function symbol first, thus clarifying that this is a function that takes 2 arguments. But okay, I'm not going to be that annoying about it, so I'll just write it the normal way with the infix notation. But that's what's really going on here, is we have this sort of undefined function symbol. And all right, what's true about this function plus? Well, first of all, let me explain how plus deals with 0, this sort of special number. And yeah, it just does what you think, right? The addition of any number and 0 is just that number. So this is kind of the base case in the definition of addition. And this is the recursive step, or the inductive step in the recursive definition of, I guess I should call it the recursive step in the recursive definition of addition. And here's what it says. It says, maybe it's best to think of it as going from right to left. If you have the successor of the sum of two numbers, then it's just one of those numbers plus the successor of the other. So if you want to translate this into something you're more comfortable with, this is kind of like x plus y plus 1, and this is kind of like x plus y plus 1. So of course that's true, but what this enables us to do, as we did once upon a time in class, is if you want to know the successor of, if you want to know, if you want to sort of understand, I guess, what 2 plus 3 is, we can understand that the successor of 2 plus 3 is just, 2 plus the successor of 3. And what is, and then that's maybe kind of it. And then well, okay, I'll stop there. Okay, so let's go. That was 5 minutes of ramble. Let's begin the proof. Prove that 1 plus 1 is not 3. How am I going to do this? Well, there's only one way, and that is to do a proof by contradiction. So I'm going to suppose that 1 plus 1 is 3. So okay, let's go. So I have the successor of 0 plus the successor of 0, that's what 1 is after all, is 3. 3 is the successor of the successor of the successor of 0. Okay, and what we want to happen sort of way down here is a contradiction, and from this we will conclude the negation of that, which, once again, not going all the way hardcore, the negation of this is just, people usually abbreviate that as the successor of 0 plus the successor of 0 is not equal to the successor of the successor of the successor of 0. Okay, but really, not equal is not actually a symbol of our language, it's just shorthand for an equal statement with a negation kind of on the outside, but I'll just be casual. Okay, let's go. How are we going to get this contradiction? Well, we just got to kind of break it down. Why is 1 plus 1 not 3? It's because 1 plus 1 is 2. So first let's establish that 1 plus 1 is 2. How are we going to do that? Well, we're going to use the recursive definition of addition. And so I kind of want to know, and so I'm working on the left-hand side now, what is 1 plus 1? Like, on some deep level, what is 1 plus 1? Well, here's how we're going to now see how axiom 4 works in action. Basically, I want to make x s sub 0, and I want to make y 0. So I'm going to, by doing this Fitch-style, this forces me to do, sort of one line at a time. So what I'm going to do right now is I'm going to set x equal to 1. Okay, and that gives me for all y, 1, I'll just pronounce it 1, plus the successor of y is the successor of 1 plus y. And what I did here is a universal elim on line 4, but maybe what you want to kind of hear is how I did that, and the answer is I just set x to be 1. So everywhere, so I think that's pretty clear, right? Because here was an x, and here was an x. Okay, and now we agreed in order to make the left-hand side of this look like the left-hand side of line 5, then what I need to do now is replace y with 0. So stick a 0 in everywhere where you see y. Okay, what do you get? Successor of 0 plus the successor of 0 equals the successor of 0 plus 0. So this is universal elim 6. And what did I do? I set y equal to 0. So I think that is hopefully pretty pretty clear that I don't think I need this color underlines anymore. You just have to figure it out. Okay, and yeah, now what? Well, I want to simplify this sort of inside here a little bit. I think that's what I want to do next. No, maybe I'll just do some kind of transitive property sort of right now or something. Is that what I want to do? Let me just remind myself what I did on my paper. Yeah, I guess maybe now is the time to do that. What have I done here? Equals this, yeah. Oh, okay. So sure. So let's simplify what's on the inside here. For that, we can use line 3. So for x here, let's stick in s of 0. Okay. So if I do that, I get 1 plus 0 equals 1. So that's certainly true. Where does that come from? That's universal elim 3. And I got that by setting x to be 1. Okay, and the idea here now is that I'm going to sort of work on the inside here. I'm going to sort of simplify 1 plus 0 into what it is, which is just 1. Okay, so now I'm like kind of a little bit stuck or something. Not stuck, but I need a rule in my formal system that I don't have because we've never really done any Fitch-style proofs with function symbols. But it is sort of built into logic, so to speak, that the function symbol returns like, a certain object. And so what I want to do right now is I want to like apply s to both sides of this line 8. So I want to assert that because of line 8, this is true. And where did 1, 2, 3, 4, 5, 6? Yeah, where did this line 9 come from? It came from just line 8. So I'm just going to write something like, apply s to line 8. And I'm going to just make a mental note later that this is something we need to work on in our Fitch-style system, to kind of account for this sort of thing, I guess. Yeah, but certainly I'm not using any facts about arithmetic here. I'm just using facts about how function symbols work, which is just a part of the logic. Okay, so now let's go to line 10. What do I want to do in line 10? Well, the whole point of all of this work was because I have this line 5. So I'll just kind of draw your attention to line 5 and line 9. This is taking forever. And what does line 5 say? It says that 1 plus 1 is... Hold on, I'm really confusing myself. Do I want to stick something back in? Yeah, I need to do a little bit more work first. Sorry. I need to do... what am I doing? Transfer 7, 9. Yeah, sorry. First, the whole goal was to simplify line 7. So let me sort of do one more thing. I think I can apply the transitive property to lines 7 and 9. That's kind of what I wanted to do, right? Because it was this kind of annoying thing here that I wanted to kind of get rid of, and maybe I'll now just sort of underline, right? That's green and that's green, and so continuing with some colors, that's purple, and that's now this is like red or whatever. So okay, if purple equals green and green equals red, then purple equals red. Okay, so in other words, I want to apply the transitive property to lines 7 and 9. So let's do that. And so I get that 1 plus 1 equals 3. What am I doing? I appear to be going round and round in circles. Oh, that's because I have an extra s here. Oh man. That's what happened. When I apply s, sorry, this is very confusing. When I applied s to line 8, that should be s of 0. I had one too many s's. Okay, so really line 9 is saying that the successor of 1 plus 0 is the successor of 1. Okay, of course that's true, duh. I just got rid of this 0. Why? Because of line 8. Sorry, that was very distracting perhaps for you. Anyway, we're back. So I have, like I said in line 7, I know that 1 plus 1 is this green thing, but I also know that this green thing is this red thing, so I therefore say that the purple thing is the red thing. So it's the successor of 0. Let me put this paper down and just trust my wits. So what is this? What is the justification for this? It's the transitive property of equality, and this is just, once again, built into the logic. If I take line 7 and line 9 and I apply the transitive property to them, then I get line 10. Alright, so we're finally ready to start doing some sort of thinking. 6, 7, 8, 9, and 10, all they did was prove from the axioms, from scratch. I mean, what axioms did I use? I used, I used 3 and 4. So this is just me recursively computing that in fact 1 plus 1 is 2. That's what I just proved, that 1 plus 1 is 2. And so now it's time to use this this poisoned assumption. The poisoned assumption is that 1 plus 1 is 3. And so the way we're going to show that 1 plus 1 is not 3 is because 1 plus 1 is 2. Alright, so now, okay, if you want to, you can simply take lines 5 and 10 and combine them together via some sort of substitution principle or something like that, and you will easily get that's 2 equals 3. But if you want to be very annoying, which I'm going to do right now, then you can actually just flip the order of line 10. So you write it instead as 2 equals 1 plus 1. Why would you want to do something like that? Well, first of all, I'm allowed to do that. This is the symmetric property of equality just applied to line 10. The only reason to do that is that now I can apply. I hope I'm doing this right. Why is it not going to... I want 3 equals 2, right? So no, I want to apply the symmetric property of equality to 5. I did that wrong. I should look at my paper. Okay, so yeah, this is just so stupid what I'm doing right now. But what I want to do is I want to apply the symmetric property of equality to line 5. You'll see why. So that will give me the successor of the successor of the successor of 0 equals the successor of 0 plus the successor of 0. Okay, it's getting a little better now, maybe. This is the symmetric property of equality applied to line 5. Okay, and now I'm going to look at lines 10 and 11, and what do I see about lines 10 and 11? Well, they can be combined via the transitive property. The point is that the transitive property actually does care sort of which side it's on, or maybe it doesn't. I guess it depends on what technical transitive property you're using. So, okay, one way or another, we're going to combine lines 10 and 11 now, and what is it going to say? It's going to say that since 3 equals this thing, and this thing equals 2, then 3 equals 2. So, all of this was just to get that 3 equals 2. Why? It's the transitive property of equality applied to lines 11 and 10. Okay, sort of in equality maybe it's sort of irrelevant because equality is symmetric, it's irrelevant sort of how you apply the transitive property. You could get lazy about it, but the true sort of transitive property says like A, R, B, and B, R, C, you know, implies A, R, C, kind of in that order, and it is sort of essential that these two things be the same. If you had some kind of system in which was transitive but not symmetric, then that would be sort of relevant. So I'm just being really annoying about that for some reason. I did want 1 plus 1 to be on sort of the right side of this, but on the left side of this. That's why I spent time doing that. Alright, worst video ever. Here we are on line 12. What have we accomplished? 3 equals 2. But notice now that we've sort of written addition out of the story, right? The goal was to show that 1 plus 1 can't be 3. Well, we've shown that 1 plus 1 is 2 using the axioms of addition. And so the real reason why 1 plus 1 can't be 3 is because 1 plus 1 is 2, and 2 can't be 3. Okay, yikes. I will finish this in a minute. Okay, we're back. Don't want to know how long it's been so far. In my imagination, it's 5 minutes. It was probably more like 20. That's terrible. Anyway, hopefully you're watching this on 3 times speed. Let's finish this off because we made it this far. I have that 3 equals 2. Well, that can't be. That's going to lead us to this contradiction. How specifically can I show that 3 is not 2? Well, I went to great lengths to get it in this exact format, 3 equals 2, and that's because you will now see one of the functions of this axiom 2, which says that the successor function is 1 to 1. And so what I want to do right now is use that over and over again. So basically, if 3 is 2, then that means that 2 is 1, and that can't be. So in other words, I want to sub in for x 2. And so I get for all y, s of 2 equals s of y implies that 2 equals y. Where did this come from? This came from universal elim line 2. And what did I do is I set x to be 2. So s of 0. Okay, and now one more time I want to set y to be 1. So I get s of 0 equals, I stick 1 in for y, so in place of y I put s of 0, and that implies s of 0 equals, what did I say? Plugging in 1 for y. Yeah. So that is, let's see if I did this correctly, that's universal elim 13, and what did I do? I set y to be 1. I think I did that correctly. Yup, and yup. Okay, and now this says, as I mentioned, this says if 3 is 2, then 2 is 1. But I have a line 12, which says that 3 is 2. So I get that 2 is 1. Alright, and what's the reason for that? Arrow, elim 1412. Okay, so is this going somewhere? Yes, it is. Now I just do it all again. So this maybe is a right amount of tedium, or maybe too much. But we have 2 equals 1. What are we going to do? We're going to again use axiom 2, or just line 2. But now in place of x, I'm going to put 1. So I get for all y, s of 0 equals s of y implies, I'm putting in 1 for x, s of 0 equals y. What's the reason? Universal elim, I went back to line 2, and how did I do it? I set x equal to 1. And now, for y, I am going to stick in 0. And I'm going to get s of 0 equals s of 0 implies that s of 0 equals 0. That is universal elim 16, setting y to be 0. And combining now lines 15 and 17 together gives me that 1 equals 0. So this is arrow elim 17, 15. And, okay, we're almost there, because this can't be. Why is 1 not 0? Because 0 is the number who is no one's successor. So I reach for line 1, and line 1 says that S of 0 is not 0. So this is universal elim line 1. Specifically setting x to be 0, although I think that's kind of obvious. Okay, and now finally in line 20 I AND those together, so I have that 1 equals 0, and it's not the case that 1 equals 0. This not equals is just shorthand for that. It has been the whole time. So that's AND intro. 18 and 19, and that is a bottom intro 20, and that's line 22. I guess that's how long it took me, yep, on my thing. And reason, it's a negation intro lines 5 through 21. Okay. Good. Let me pause this and I'll come back and do the back. Okay, we are back. I'm going to do the back of this worksheet now. So we're continuing to do proofs in Peano Arithmetic using the logical structure of the Fitch-style proof system to make sure our proofs are completely rigorous. And yeah, we want to prove something now, which is, I think this is quite hard to do. The thing we want to prove, let's see, I'll put the theorem up here. The theorem that we'd like to prove is that for all numbers x, it's true, let me make sure I say this exactly correctly. Yeah, the successor of that number is not that number. So no number is its own successor. Okay, this is so intuitive that on the day that we were discovering, kind of by screwing around, what do we think the Peano axioms should be, this is one of the axioms that people put forward, this is one of the ideas that people put forward as a potential axiom, that you can't have a number sort of pointing back to itself. So it turns out that we don't need a special axiom for this, because more generally we need the successor function to be 1-to-1, and it's kind of a consequence of the 1-to-1ness of the successor function that this is now a theorem. Okay, what makes this theorem quite hard to prove, harder than any of the theorems we've proved so far, is because every other theorem we've proved so far in this class, well, we did a whole bunch of them casually on the Peano Arithmetic day, and then we just did one formally, which was on the previous page, but it was still kind of a finite fact about specific numbers. We proved, I think, in class, that 2 plus 3 is 5, and just on the front of this worksheet, we proved that 1 plus 1 is 2, and therefore that 1 plus 1 is not 3. But, okay, those are just kind of finite facts, and of course that Peano Arithmetic is powerful enough to prove all of these infinite number of finite facts about the numbers, but if it's really an axiomatization of arithmetic, then it should be powerful enough to prove all true statements of arithmetic, including universal statements. So how can we prove sort of these universal statements of arithmetic? And the answer is mathematical induction. Mathematical induction is, in fact, the thing which enables you to ever prove statements about all numbers. And okay, repeating what I said half an hour ago, that you really understand axioms only when you use them. We will hopefully, the goal of this problem on the back here is to understand mathematical induction by seeing how it gets used. Okay, well, what is mathematical induction? A prerequisite for this class is that you all did this. You either did this, my students did this in Pre-Calc C or in functions, or perhaps again in discrete math. But the way we teach mathematical induction is to say, well, you have some kind of property, and you establish that the first number you care about, say 0 has that property, and whenever a number has that property, the next number has that property too, therefore all the numbers must have that property. So we probably wrote something like this. We said that, okay, suppose 0 has that property, so you got to prove that. That's called the base case. And let's say, I guess it doesn't matter what letters I use and stuff, but let's just say for all, I'll just use x. For all x, whenever the property holds of a number, then it holds of the next number. So that property should be true of the successor of x. If that's true, this is the base step, this is the inductive step, and what mathematical induction says is that if you've shown that 0 has the property, and you've shown that the property is always inherited from one number to the next number, then, putting brackets around this, we conclude that, in fact, all numbers have this property. Maybe it's better to use another variable here. It doesn't matter, but I'll just call it y. Okay. That is probably how I stated induction when I taught it, back in pre-calc C, or maybe not even. But of course, the idea of mathematical induction as an axiom is that we want this to be true for all possible properties. So in a casual context, or if you're doing a certain kind of piano arithmetic, then you just throw a quantifier out in the front of this entire statement to assert that this is supposed to be true for all possible properties. But of course, what is this for all possible properties? That's kind of a crazy thing that we've never seen before in this class. We are somehow quantifying over properties, and I don't even know what that means. Or I kind of do, but not to the same level of understanding that I have for quantification over objects. So here, it's understood that when you see these universal quantifiers, that they're quantifying over the objects of our domain of discourse, in other words, the natural numbers. That is what second order logic is. Second order logic is a more advanced logic, which is going to require its own proof system, presumably, and it's going to have its own semantics and its own kind of rules and its own kind of properties. And the second order logic is going to allow you to quantify over predicates. Okay, for various reasons, we don't want that. We want to do things in first order logic. So how can I retain the power of induction, but avoid quantifying over predicates? The answer is this thing called an axiom schema. And okay, I taught you this, but I forgive you for having no idea what I was talking about at the time. An axiom schema says that for every possible phi, we have an axiom of the form, and now I just copy this right above. So in place of p, I have phi of 0, and for all x, phi of x implies phi of s of x, and if that's true, then we're going to conclude that all numbers have property phi. Okay, well, so what I'm really doing, the solution to this is somewhat crazy. The solution to avoiding second order logic is to have an infinite number of axioms. And that's not kind of as crazy as it sounds, because though there are an infinite number of them, there are sort of a countable number of them. Because what actually counts as a property is simply a predicate. And a predicate is simply a well-formed formula with one free variable. And how many of these predicates are there? Well, you can sort of syntactically characterize these predicates as just being themselves finite strings of symbols, and you can characterize the notion of what a free variable is. And so in fact, because there are only a countable number of strings in my language, then there are only a countable number of first order predicates. And so we have in fact a countable number of these axioms, and you can sort of zigzag your way through all of them. And so it's not as much problem as you would think to have an infinite number of them. Okay, but it does make things kind of a little bit weird. So, all right, if you had no understanding of this previously, then this is your chance to understand it, and you still might not understand it. So let's do the problem. And what I say here is okay, we're going to prove this fact that no number is its own successor. Let's finally kind of get going. We have a couple of axioms of Peano arithmetic that I need. I have this one that says that it's never true, that the successor of a number is 0. That's going to come up in this proof. I'm going to use the one-to-oneness of the successor function. So that's something. Okay. And now I say, perhaps cryptically in the directions, that you should write your own axiom 3. And your own axiom 3 is going to be one of these infinite number of induction axioms, first order induction axioms. And so I think what I said on the paper is literally like define phi to be this. So that's what I'm going to do, right? I'm just going to let phi of x be let phi of x be the predicate. S of x is not equal to x. In other words, everywhere you see, so if you just think of S of x is not equal to x as a well-formed formula, it is a syntactically well-formed formula, but it's a syntactically well-formed formula with a free variable x. And so it's an example of one of these, kind of predicates. And so since it's a predicate, there will be an axiom of induction associated with it. And so the particular one of these infinite number of first order induction axioms that I need is the one that says about the particular property of which I am interested in induction. Okay? So that is to say, if this property in the green box is true of 0, so if S of 0 is not 0, and so that's the base case, which is and for all x, now here I just insert S of x is not equal to x. That's like my property. When that's true, it's true of the next number 2, so it should be true of S of x. So S of x is not equal to S of x. So what did I just do here? I simply substituted in the successor of x everywhere I saw an x in the green box. Then for all y, that property is true of y, that the successor of y is not y. Assume everything's still being captured here. Okay, and that is all I need to do this proof. So, though Peano arithmetic has an infinite number of axioms, in any given proof, since a proof must be finite, a proof can only use a finite number of them. And this proof, in particular, is only going to use 3 axioms. The fact that 0 has no successor, the fact that the successor function is 1-to-1, and the fact that induction holds for this property. Okay, and the good stuff that we want, the entire conclusion of our argument, is this consequent over here. And that's just how induction works, right? When you want to prove something by induction, you prove that it's true for 0, you show that the property is always inherited, and then you conclude at the end of the argument the thing that you want. And so the very thing that we want, the entire goal of this proof, is this blue underlined thing, so I just need to prove the antecedent of this conditional. Okay, and now I just know exactly what to do. The first thing I need to prove is that the successor of 0 is not 0. Well, that's what axiom 1 tells me. And axiom 1 tells me that no number has a successor which is 0. So in particular, 0 doesn't. So I state that successor of 0 is not 0. Justification, universal elim line 1, and it's me setting x to be 0. Okay, base case done. Now comes the inductive step. Well, the inductive step is this universally quantified conditional. So of course, how do we do that? What did I do in my paper? Yeah. on my paper, I just started a universal proof. So pick an arbitrary name symbol A, and what I want to prove about that arbitrary name symbol is this conditional. In other words, I'm going to assume here in line 5 that the successor of A is not A. The successor of A is not A, and I'm going to conclude, this. Okay, and so the proof is going to go like this. Maybe I should sort of finish it off from the inside out. Maybe that's a good idea. So I don't know what line this is going to be, but what I'm hoping to show is that the successor of A, I hope that's enough room, probably is not equal to the successor of A, which will enable me to conclude the conditional that if the successor of A is not A, in other words, if the property holds for A, then the property holds for the successor of A. And if that's true for an arbitrary A, then I will conclude that it is in fact true for all x that when the successor of x is not x, then the successor of x is not the successor of x. And that will get ANDed together with line 4. So S of 0 is not 0, and here is the inductive step, maybe this is kind of weird to be going outside in this case because the tension is being broken or whatever, but this is the whole thing, and by doing that I can now conclude for all y, S of y is not y. Okay, so now I just need to fill in the blanks. This will be helpful to some people to do it in this kind of order, I guess. So why is this true? Well, I need to prove this thing, which is in fact a negation, because really this not equals is not a primitive. It's just the negation of the equality, and so that suggests that I should do this by contradiction. So in line 6, I shall assume that the successor of A is the successor of A, and now I'm going to hope for a bottom. Well, where is that bottom going to come from? Now I reach for axiom 2, and I say if the successor of A is A, then what? Well, sticking in for x, S of A, so I get for all y, S of A equals S of y, implies that the successor of A equals y. So what I do here, this is another universal elim 2, and what I did was to set x to be the successor of A. And now I'm going to stick in for y, A, I guess. Yup. And so I get that the successor of A equals the successor of A, implies that the successor of A equals A. Reason universal elim 7. This is me setting y equal to A. And okay, now I have a conditional, and my assumption, which is going to lead to a contradiction, was line 6. But, right, what this says is that, okay, I guess I can just do it, right? The successor of A equals A. What's the reason? X is arrow elim 8, 6. So that tells me that the successor of A is A, but that is precisely what I know to be false, because it's the negation of line 9, which is in fact the inductive hypothesis, actually, of my inductive step. Whew, this is I guess this is pretty hard. So S of A equals A, and maybe it's helpful if I rewrite line 5 as not, S of A equals A. Reason and intro 5, 9. This is a bottom, so I get bottom intro 10. Then here in line 12, I have done a proof by contradiction. I assumed something in line 6. I got a contradiction, so this is negation intro 6 through 11. And then I conclude in line 13 that I have indeed shown for this arbitrary A the inheritance of this property, right? I assumed in line 5 that the property held for A. That was my inductive hypothesis. I now show that the property holds for the successor of A. So this is arrow intro 5 through 12. And now, here in line 14, I simply conclude that A was arbitrary. So by universal intro 5 through 13, this holds now for arbitrary X. But this is exactly the inductive property. So I AND this together with line 4, and that's what this is. This is AND intro 4 and 14, and that entire line 15 is the antecedent of the conditional in line 3. It just is. Therefore, by arrow elim 3 and 15, I get that this property holds. Okay, so this shows, hopefully, how what mathematical induction is, why it's kind of simpler somehow to state induction in second-order logic, why, however, we want to do it in first-order logic because we have rules for first-order logic, what it means to have an infinite number of axioms, and how I can still sort of do the proofs by grabbing the specific induction axiom that I need for the property under discussion. And this shows how to do a proof by induction within Peano Arithmetic in the Fitch-style system. Okay, goodbye!